Are asking if this series is going to converge absolutely, and that means in absolute value, or does it converge conditionally? The difference between these two is there are times when a series has positive and negative values. So when it has positive and negative values, well, of course, some of those negative values will take away from the positive values, making the overall sum smaller. So it's possible that with the positives and negatives, it converges. But if you have absolute value, in other words, you only have positive values, then does it converge or diverge? So converge conditionally means it would converge with the positive and negatives. Converge absolutely would mean that it converges even if you only have positive values. And then, of course, diverge means that it would add up to infinity. In this case, we don't have any positive or negatives. If it was natural log of something less than 1, we might have negatives, but in here we don't have any negatives, so we just have to figure out, does it converge or does it diverge? I'm going to be using the ratio test, where you take the n plus first term divided by the nth term, so in other words, the ratio of one term to the one that's going to come after it, and then take the limit as n goes to infinity. Now technically you're supposed to take the absolute value of this, but as I just said, we don't have any negatives, so I'm not going to have to do the absolute value. But if you take that limit and it's less than 1, then the series converges. If it's bigger than 1, including infinity, then it diverges. The sad thing is, if it equals 1, this test is not conclusive. So if it were to equal 1, we would then have to do something else, some other test. So let's see, this is going to be the n plus first, so put an n plus 1 in for all those n's. And it's going to be sort of a big fraction. So in the numerator is going to be n plus 1 over the natural log of n plus 1 to the n plus 1, and then divide by the nth term, and then when you're dividing two fractions, you invert and multiply. And after you've done this first step a few times, I would suggest that you just skip this step and go to this step. So it's going to be this term right here, so the n plus 1 over the natural log of n plus 1 to the n plus 1, and then invert and multiply, and it would look like that. And another good thing to do is give some indication of what test you're using, because we've got integral test, root test, ratio test. We've got all of these tests, and it's good to know which one you're using. So now we could reduce. So there's n of these things that can be canceled. So cancel, and that will cancel n of them, but it will leave one of them in the denominator. So for the numerator, we've got n plus 1. We've got this n, and there's the natural log of n plus 1, and there's just one of those. So notice that these two things, n plus 1 and n, they basically balance each other out. If it was just that, and n is going to infinity, the answer would be 1. But this even has more in the denominator, so then it's going to be 1 divided by something, and that something is going to infinity. So we're essentially ending up with 1 divided by infinity, 0, which is good news. That means it converges. Now we actually have to prove that it equals 0. So this would be infinity plus 1, also known as infinity. This would be infinity times infinity, so that means it's infinity over infinity, so we're allowed to use L'Hopital's rule. The top, that's easy to take the derivative of, 1. For this, though, we'll need to use the product rule. So take the derivative of n, leave the natural log function alone, plus leave the n alone, and take the derivative of the natural log function, and then we need to clean that up because it's a compound or complex fraction. So multiply the top and the bottom by n plus 1. So we've got the limit as n goes to infinity. The top now has an n plus 1. The bottom has n plus 1 times the natural log of n plus 1. And these cancel, so it leaves an n. Well, I'm pretty sure that this thing is going to 0, but L'Hopital's rule took something that looked like this and made it look like this. And that is actually more complicated instead of less complicated. So I will try L'Hopital's rule one more time, but if it gets even more complicated, then L'Hopital's is not helping us. We'll need to try something else. So try L'Hopital's rule again. So the derivative on the top, again, will be 1. The derivative here, right here, we need the product rule, so take the derivative of this is going to be a 1, then times natural log. And then leave this alone and take the derivative of this. So that's going to be plus an n plus 1 left alone. The derivative of this is going to be 1 over n plus 1. Oh, excuse me, this is supposed to be times. 1 over n plus 1. Whew. And the derivative of this is 1. Yay, it worked! Because this time, when we have this compound fraction, it cancels. So then we're left with the limit as n goes to infinity. Good old L'Hopital. 1 over, we've got the natural log of n plus 1, and then a 1 plus a 1. Okay, so now let n go to infinity. Natural log of infinity is infinity. Plus 2 is infinity. 1 divided by something infinitely big makes it infinitely small, 0. And so, since that is less than 1, therefore, the series we're talking about converges. Adds up to a finite amount. And technically, you could say it converges absolutely, because if you were to take absolute value of this, it's the exact same thing.